Hi everyone. Now we'll be going through the ideal gas part, which is in the mole concept notes. So in the chapter topic A, whereby you have the stoichiometry notes, we have this section on gases that is not being covered. So therefore, we are going to cover this as an e-learning topic. So turn to the pages on gases in your notes so that you can follow the lesson, or you can refer to these PowerPoint slides. After going through this recorded lesson, you may want to revise and by going through your notes, the relevant section that is related to ideal gas. And after reviewing the lesson and the notes, you will take I don't think you will take a quiz, but you will be doing an assignment to assess your learning and to check your understanding. So firstly, we look at the behavior of a gas. So in the behavior of the gas, there's some assumptions that we'll make in the kinetic theory of the gas so that we can understand it better. And these are some of the assumptions. So first, we are assuming that gases are very, very tiny particles and they are taking up. They themselves has a negligible volume. So what do I mean by that is look at this picture, okay? So if this is the volume of the container, the total space in the container, let's say, is 100 cm cubed. Okay? And in the container, there are gaseous particles. Whenever we are doing calculation, we are going to be using the volume as 100 cm cubed. But if you think about it, the actual volume that the gases are able to move around is not 100 cm cubed, but is 100 minus the volume occupied by this yellow balls of gases, right? So the actual volume that the gases can move around in the container is not 100, but lesser than that. And it can be represented by all these green areas. Right? So the green areas are the actual areas that the gas particles can move to. But we are not going to do that. We are still going to use 100 in the calculation following the container volume because we are making this assumption that the gas particles are so tiny that the volume that they are taking up is negligible. So the yellow portions that they are taking up in the picture is considered insignificant. Okay? So therefore, the overall space that the particles can move is the same as the container volume and is 100 cm cubed. So that's the first assumption. Second assumption is that the gaseous particles are very, very far apart and in between them, there's totally no attractive forces. So we are imagining a space like this and the particles are very, very far from one another. Okay, because if we're assuming that they are very near one another, then between the particles, there will be something known as intermolecular force. Right? But the assumption behind the gases that we are using is that the gaseous particles are very, 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 very far apart. And therefore, in between them, there's totally no attractive forces of attraction. Okay, so we are imagining the case whereby there's no intermolecular forces between gases. Okay, so of course, this assumption sounds a little bit unreal. Just like the same previous assumption that the gases are actually not taking up any space or any volume, and the actual volume that it can move is the same as the volume of the container, right? So because of all these assumptions, we'll find that in reality, the gases do not really 100% follow what we have, the laws that's governing the gases. So to some extent, sometimes some gases do deviate from the law because they may not exactly follow these assumptions. Okay, but we will still have to make such assumptions in science. And the reason for still making such assumptions in science is mainly to simplify things. If not, the whole thing will be too complex and we will not be able to come up with a trend or theory to explain it. So we'll try to make these assumptions to simplify the context, the calculations, so it's more manageable. Okay, other assumptions that is made behind the behavior of the gas includes that the gases are always in constant random motion, and when they bump with each other, they also bump with the walls of the container. And if they happen to do so, every collision is perfectly elastic. So what's the meaning of perfect elastic collision? That means, right, when they collide with each other or collide with the walls of the container, there's no exchange of energy. So the gases did not lose any energy before and after the collision. So, but of course, we learn in physics that energies are converted from one form to another. And therefore, we do expect that there will be energy loss in terms of conversion in reality. But to simplify matter and to make it easier for us to come up with a model that describe all the gases, so the kinetic theory of gases will assume that they are in constant random motion, and as they collide, there will be no exchange of energy, and therefore they are perfectly elastic collision. There will be no loss of energy. Okay, and lastly, the average kinetic energy of any gas particles is directly proportional to the absolute temperature. So absolute temperature here refers to temperature in Kelvin. Okay, it refers to temperature in Kelvin. So if you remember, I illustrated this before. So if I have a vessel of nitrogen gas, and I have a vessel of hydrogen gas, and I have a vessel of oxygen gas, in all of these gases are at, let's say, 350 Kelvin. So will the average kinetic energy of these gases be the same? Yes, they will be the same. So despite that the identity of the gases are different, the mass of the gases are different, the average kinetic energy of the gas particles is only proportional to the temperature in Kelvin. So since temperature is 350 for nitrogen, for hydrogen, for oxygen, so therefore the average kinetic energy of all these gases is the same. Okay, it will be the same. So it will only change when the temperature changes. But of course, as I mentioned before, we recognize that certain gases are heavier, like oxygen has a mass of 32 versus hydrogen, which has a mass of only 2 grams per mole. So the average kinetic energy is the same because it depends on only temperature. However, the speed of the molecules will be different. The lighter molecules will move faster, whereas the heavier molecules will move slower. Okay, so that's the 5 assumptions behind the ideal gas, behind the kinetic theory of gases, and we make use of these 5 assumptions to understand gases better. All right, so this is an illustration of assumption 1 and 2. So assumption 1, the particles occupy such a small volume such that we can ignore the amount of space that they're taking up, and we just use the volume of the container. So the actual full sentence is that gases have negligible volume compared to the volume of the container. Okay, so it's the volume that is taking up is insignificant. Gases are very far apart, so there's no intermolecular force between the molecules or the particles. And they're always moving, bumping into each other, and even if they bump into each other, there's no loss of energy. There's no transfer of energy. Every collision is perfectly elastic. Now, it is the action of the gases that is bumping against the wall of the container that gives rise to a pressure. Right? So gases exert a pressure because they always collide against the container wall, and therefore they exert a force on the container. And the force exerted per unit area of the container is defined as the pressure of the gas. Okay. And you look at the gases movement, they are always in constant random movement, but they are always moving in straight line. So they're always traveling in straight line until the path meets something. Either they meet another molecule of gas, or they meet the wall of the container, and then they change the path. Okay, so if there's nothing blocking them, they will just continue to travel in straight line. But if it's colliding with another particle, or another particle comes in their way, and therefore they will be moving, they will be diverted, but they will still continue to move in straight line. So as the colloid is perfectly elastic, there's no loss of energy. So the kinetic energy before and after the collision remains the same. And the average kinetic energy is only dependent on the absolute temperature, which is the temperature measured in Kelvin. Next, we also learn from Avogadro's laws of gases. So Avogadro states that 1 mole of any gases occupy a certain volume under a certain condition. And that volume is known as the molar volume. And the actual value of the molar volume is dependent on the temperature and pressure conditions. So at standard ambient temperature, at standard temperature and pressure, standard temperature and pressure here refers to your STP. Okay, so for STP, the molar volume of the gas is 24 dm cube per mole of gas, or 22400 cm cube per mole of gas. Okay, and this is at standard temperature pressure, STP, which is 0 degrees Celsius and 1 atm. 0 degrees Celsius is 273 Kelvin. At room temperature, it is 24 dm cube. That's what you have been learning. It's 2298 Kelvin and 1 atmosphere, and the molar volume is 24 dm cube. That means 1 mole of any gas will occupy this volume of 24 dm cube, or 24000 cm cube. So regardless of the identity of the gas. So that means, right, if I have 1 mole of helium in the balloon, or I have 1 mole of hydrogen in the balloon, or I have 1 mole of oxygen in the balloon, the volume occupied by the gases in the balloon is the same. Because if this is 1 mole, and this is 1 mole, and this is 1 mole, 1 mole of any gas under the same condition has the same molar volume. So if it's at room temperature pressure RTP, then this 1 mole will have a volume of 24 dm cube. This will also be 24 dm cube, and this is also 24 dm cube. So it is not dependent on the identity of the gas. It's only dependent on the pressure, temperature that affects the molar volume value. So take note that for IB, there's 1 more. They correct the standard ambient temperature. Let me write down. They correct the standard ambient temperature pressure. So the condition is called SATP, standard ambient temperature pressure. And standard ambient temperature pressure, the molar volume is 24.8 dm cube. Okay, so take note of this also. Okay, so if we look at these two diagram, we can see that since the volume is the same, so the moles of gas should be 1 mole, right? So molar volume is constant for the gases. So therefore, because of Avogadro's law stating that 1 mole of any gas under a certain condition should have the same molar volume, therefore mole ratio equals to volume ratio for gases. So for example, if I have this amount of gas in the vessel, I have 48 dm cube in the vessel, right? And I have another vessel which has 24 dm cube of gas. So the mole ratio, let's say it was 2:1. You can see that the volume ratio will also be 2:1. Okay, so for gases only, mole ratio equals to volume ratio, because per mole of gas occupies the same molar volume. Okay, so you can see over here, since the volume are all 24 or 22.4 dm cube, although the identity of the gas has changed, right, but they are still having the same molar volume per mole of gas, because it's only dependent on temperature, and 0 degrees over here is referring to 293 Kelvin. So volume of the gas at a given temperature and pressure is directly proportional to the number of moles. So the greater number of moles, the greater the volume. So under constant P and T, volume is directly proportional to moles. So if I have 5 moles of gas, I will expect the volume to be bigger proportionally compared to 1 mole of gas. So it's not dependent on the identity of the gas at all. It's just dependent on the temperature and pressure condition. So Avogadro's law states that an equal volume of gas measured at the same temperature and pressure will contain the equal number of molecules. And because number of molecules divided by Avogadro's constant is the mole, and Avogadro's constant is the same value, so we can say that even equal volume of gases measured at same temperature and pressure will contain equal moles. And the volume, we give it a special name, and the name that we're going to give it is called molar volume. So the volume occupied by 1 mole of any gas at a particular temperature and pressure is given the name called molar volume. Okay, so to understand gases better, we have to make some prediction, assuming that all the gases are behaving ideally. So what do you mean by gases behaving ideally? Remember the 5 assumptions on the kinetic particle theory of the gas? So we are making these assumptions, applying all these 5 assumptions, and if the gases follows exactly these 5 assumptions in their behavior, then the gases is actually an ideal gas. So it's behaving ideally. So when we derive this ideal gas law, or when they make predictions or a model, they assume that the gases are ideal. Okay, so this makes it easier, and the situation becomes less complex in order for us to understand gases' behavior. So definition of an ideal gas is a gas that obeys all the 5 assumptions of the kinetic theory of gases, and an ideal gas will obey this ideal gas equation, PV equals to nRT. Okay, so let me explain what is PV nRT to you. P stands for pressure, V stands for volume, N stands for number of moles, R is known as a gas constant, and because it's a constant, so the value is 8.31. It is a fixed value for under a fixed condition, and temperature here is the temperature in Kelvin. So the product, that means pressure times volume, must equals to number of moles times the gas constant times temperature. All right, so what do we need to take note when we're applying this PV equal nRT equation is we need to take note of the units. So the units of temperature is always in Kelvin. The gas constant value commonly that we are using is 8.31, and this can be found in your data booklet. If you have forgotten the value, you can refer to data booklet. N is the number of moles. And pressure here has a special unit, right? So it's not any units. It must be Newton per meter square. Okay, so pressure here must be Newton per meter square or Pascal. So another word for Newton per meter square is Pascal. So what happens if the pressure is in other units like ATM? Then you will need to do a conversion to Newton per meter squared or conversion to Pascal. Okay, so if the pressure given to you is kilopascal, you cannot sub in directly. You will have to convert it into Pascal. Now, the volume is the one that will go wrong. So please take note about the volume. Okay, this is where most people forget about the units. So the units of volume here is not dm cube. It is not dm cube. It is meter cube. Meter cube, because the pressure is in meter. So therefore, the volume has to be in meter cube. Okay, but very often we are so comfortable with dm cube and dm cube from concentration, from calculation of moles. You know, in the stoichiometric calculation, we always move per dm cube. So we are so comfortable with it that we always use dm cube here. And that's where the mistake is. It has to be meter cube. All right, so therefore you must know how to convert dm cube into meter cube. You must know how to convert cm cube into meter cube. All right, 1 meter cube is 1000 dm cube. 1 meter cube is 1 million cm cube. Okay, so must know how to convert units. Okay, so in a way, we mentioned that ideal gas, an ideal gas is a gas, right, that obeys all the assumptions of the kinetic theory of gases, the 5 assumptions, and it obeys this equation PV equals to nRT, right? But in real world, the gases may not totally behave that way, and therefore we call them real gases. So in reality, most of the gases deviates from this ideal condition, so we give them a name called real gases. Okay. And what makes real gases deviates from ideal gas? Okay, because not only 2 of the assumptions are not entirely true, but mainly because of these 2 assumptions, is that gases do not occupy any volume, right? So the kinetic particle theory assumes that all the space available for molecules to move, it follows the container volume. But if we combine all these gas particles together, you can see that the effective space that the gases can move is only the area in green, which is actually much smaller, right? So in fact, the amount of available area is only the part in green because the gas molecules itself takes up a certain volume, but we are ignoring that. And second, assumptions that is not entirely true that cause a deviation is that attractive forces do not exist between molecules. Remember, we say that the gaseous particles has no intermolecular force. But in the real world, between molecules, there are intermolecular forces, right? And what are the intermolecular forces known called? So usually, if let's say I have a hydrogen and a hydrogen molecule, in between the molecules, there'll be intermolecular forces. Okay, and for most molecules, they are non-polar. So therefore, the name of this intermolecular forces is usually London dispersion force. London dispersion force. Okay, so there are intermolecular forces between the particles, and how does it affect the behavior? It brings them close together, right? It brings them close together. Okay, so if we put them side by side, you can see that there are some assumptions that are untrue, and that cause the real gas, or when we carry out an experiment, we'll find that sometimes the results that we get do not follow the ideal calculated values that we will be getting. So the ideal gas gives us the theoretical value. But when we conduct an experiment, the experiment gives us the real value reflecting the behavior of a real gas. But is there a way to make the real gas behaves more ideally? Right? Because if they could behave more ideally, then we will have a case of an ideal gas, right? So yes, there's a way to make them behave more ideally. That is, we adjust the surrounding conditions. And how do we adjust the surrounding conditions? We can increase the temperature. Okay, by increasing the temperature, the real gas will therefore behave more like an ideal gas. Besides increasing the temperature, what else can we do is that we can lower the pressure. When we have a lower pressure, we will find that the gases actually behaves more like an ideal gas. So we can actually create that by varying these two conditions. Okay, let me explain to you briefly why. Because first thing, at higher temperature, the particles are always moving because you have high kinetic energy, right? So in the real gas, what happens is that there are intermolecular forces between the particles. There's attractive force. But if you heat up the particles so much that they move so fast, what will happen is that the high kinetic energy or the high energy of particles will cause this to be broken. It will just move away, right? And the forces will be overcome. So by providing a very high temperature, we are able to present a condition of a gas constantly moving in high energy. Before any attractive forces can be formed, they are gone, they are moved to another place in a constant movement. And any attractive forces which are weak will be overcome by the heat. The heat energy will overcome all these forces. So by heating, it can help us to achieve this condition of this negligible attractive forces between particles. Okay, next, besides heating, how about the pressure part? How does the pressure comes in? Now, when we have a low pressure, usually we will have a very high volume. Pressure and volume are like inversely related. So when I have a low pressure, I have a high volume. Then that's what? The volume of the container is very, very large. Compared to a tiny container, this is the tiny one. And this is a very large one, right? So when we have a tiny container, the pressure is high because the particles are always hitting against the container. When we have a large volume like this, the pressure is low. Right? And now can you imagine there are 3 gas particles here? And same, there are 3 gas particles here. Right? But you can see because the container has such a small volume, the volume occupied by these 3 particles is significant. It's quite significant. So let's put in numbers so that we can see better. So if we take that this vessel is 10 cm cube and the particles occupies 3 cm cube in total. So the volume occupied by the particles in this case is already 30%, right? So we cannot say that it is negligible because 30% is substantial, right? But if we look at a bigger container, let's say this is 1,000, and this is still the same, 3 cm cube altogether. So 3 out of 1,000 is insignificant compared to 30%. So in a way, by increasing the volume of the container and lowering pressure, we have created the conditions to make the volume negligible. And so the real gas will therefore the real gases will therefore have a negligible volume compared to the volume of the container. And so it fits the definition of all the assumptions behind an ideal gas. Okay, so if you look at this graph, how do we interpret this graph? So remember the formula PV equals to nRT. So if we let n equals to 1, okay, then therefore PV over RT equals to n, and that is equals to 1. So we look at here, and that's our PV RT, and that's 1. So we look at this. So this is 1 mole of gas. Now, if the gases behaves ideally, based on the equation PV equals nRT and n equals to 1. So this line here is the line where the gas will behave ideally. because that is where n is equals to 1. So this line is where ideal gases, the gases behave ideally. So let's look at this graph and see how do we interpret this graph. So if we fix a pressure, and we vary the temperature. So what do we see? At 600 atm, if my temperature is 1000, I'm quite close to the ideal gas. At 600 atm, if my temperature is 200, I'm quite far away from the ideal gas. So when I'm very far away from the ideal gas, means that I'm deviating from the ideal gas. So you can see in this example that the higher the temperature, the closer the line is to the ideal gas line. So the gases is behaving more ideally. All right, so that's how we interpret the temperature part. Next, we will have to look at the pressure. So if we look at the purple line only, everyone just look at the purple line. Okay, so we fix the temperature in this case. And what do we see? We see that at high pressure, 900, that's the gap from ideal. But at 300 pressure, the gap is smaller. So we can see from here is that as the pressure decreases, the line is closer to the ideal gas line, which means that the gases are behaving more ideally. Okay, so to summarize, at low temperature, the low temperature is not what we want. We want high temperature. But so when you read this, of course, you can reverse the thing and then understand why it behaves more ideally. Okay, or if you follow the slides, it's trying to explain to you why it doesn't behave ideally. So at low temperature, the molecules has very low kinetic energy. They do not overcome the intermolecular force, so intermolecular force becomes significant. Okay, at high pressure, look at this picture before and after. So this is low pressure condition. This is high pressure. Look, all the particles are so close, pressurized together and occupying a very small space, constant hitting against the wall, right? So at high pressure, you'll find that the gases usually occupies a smaller volume. And what will happen is that the volume occupied by these red color bubbles will not become negligible. It will become significant. It's no longer negligible compared to the container. All right. Okay. So next. Okay. So previously we seen the effect of temperature and pressure, and the graphs, right, are for the same gas. So that means the purple line is the same gas as the red orange line, and it's the same gas as the blue line. So what is changing in this picture was the temperature, was the pressure, right? So we've seen that trend here. Now, the next graph that I'm going to show you looks a bit the same, but you can see that this time round, there are different gases. So the blue line is the CO2 line, then the orange one is for the hydrogen, the purple one is for the methane, and the yellow one is from the nitrogen. So how do, and they are at the same temperature, constant temperature. So how do we look at this? Okay, so the dotted line is the ideal gas. So if the graphs are very close to this dotted line, that means it's behaving quite ideally. Okay, so let's fix a pressure at 400. So we will even make the pressure constant, temperature constant. The only change is the nature of the gas. So we can see that at 400, this is where CO2 is. And this is where N2 is, and so on. Okay, so if you don't want to look at 400, we can also change another pressure. Let's look at maybe 600. So if we look at 600, this will be where CO2 is, and then this will be where methane is, and this is where N2 is. So again, the same thing, the further they are from the dotted line, that means the greater the deviation. So in this case, we are seeing that it seems like the nature of the gases do have an effect on the deviation, right? Because the gases deviates differently. So what is the key thing that is affecting the deviation here is that when you have different gases, they have different intermolecular force and different strength of intermolecular force. So those with greater intermolecular force, for those gases that you have greater intermolecular force, you will see a greater deviation from the ideal gas line. Okay, so those if you have greater intermolecular forces, you will lead to a greater gap or difference from the ideal gas dotted line. Okay, so that means that the nature of the gas and the intermolecular forces do have an effect on whether it will behave ideally or not. So usually gases like hydrogen, nitrogen, oxygen, they don't really deviate a lot. But the heavier the gases, the greater the deviation. Because the intermolecular forces increases as the MR of the gases increases. Okay, let me write it down for you. Intermolecular force increases as the MR of the gases increases. So the heavier gas tends to deviate more from ideal gas compared to the lighter ones because when the gases are heavy, they will tend to have greater London dispersion force or intermolecular force, and then it doesn't fulfill the assumption that they have negligible force, and so they will not behave as an ideal gas, but behave more like a real gas. Okay, so this part on Maxwell-Boltzmann, I think I can skip, right? Because I already went through Maxwell-Boltzmann with you on the shift and the graph, okay, in kinetics. So I'm going to move on to the ideal gas law. So remember our ideal gas usually will have to follow ideal gas law, and the ideal gas law is PV equals to nRT. So if it is an ideal gas, it will follow this equation very closely. Okay, P here is pressure, and pressure units is Pascal or Newton per meter square. Newton per meter square is Pascal. Volume here is meter cube. Remember, it's meter cube. Okay. Temperature is in the absolute temperature in Kelvin, and N is the number of moles. So we can, once we know three of the unknowns, we will be able to find the other unknown, right? That means if I know V and RT, I will be able to calculate P. Okay, so do take note that the volume is in meter cube and you must be able to convert. So meter cube can be converted into dm cube and cm cube. So your cm cube can be converted into meter cube. Okay, 1 meter cube is 1 million cm cube. All right, and 1 meter cube is 1000 dm cube. So do note your conversion. Temperature, if your temperature is in degrees Celsius, you can actually convert it into Kelvin by using your degrees Celsius temperature plus 273. Okay, so then you can do your conversion, and the temperature conversion is not directly proportional because it's by adding a factor. Whereas the other conversions are usually by multiplying by a number or dividing by a number. So the other units conversion for pressure and volume are usually proportional, but the conversion for temperature is not proportional directly because it's not by a multiple, but by adding a value to it. Okay, so units for pressure is Pascal or Newton per meter square. So it is not really ATM. So can you please take note, it's not really ATM, it's Pascal or Newton per meter square. And 1 Pascal is 1 Newton per meter square. But you can see that 1 atmosphere, 1 ATM is 1.01 times 10 to the power 5 Pascal. So if our question was given in ATM, we will have to convert it into Pascal first before we can sub in into PV equals to nRT. So after you sub in, then we sub in the value of the Pascal into the equation. Okay, so if we look at the R value over here. R is 8.31 joules per Kelvin per mole. All right. Now, so whenever we are using 8.31 and whenever we are pressing this number into our calculator, the units must follow what is given here. I repeat. So if your calculation involves keying in this value 8.31 into the calculator, that means you must strictly follow these units here because the 8.31 is a constant because it follows these units. If any of the units here are changed, then the value is no longer 8.31. All right, but so most of the time we use 8.31 and therefore we must follow these units. However, if there's a calculation and you did not key in the value 8.31 in your calculator, then there is no need to convert to these units. Okay, I repeat that. If there's a calculation and you did not key in 8.31 into the calculator, then there is no need for you to keep strictly to these units anymore. I'll show you some examples later. Okay, so now let's try to plot a graph and look at the different type of graph. So if I'm going to plot one for 1 mole of gas, so N is 1, right? And I shift the T over, so PV over T. So PV over T equals to NR. N is 1, R is 8.31. So the values on this side is 1 times 8.31, and this is not going to change. So it's a constant. So I can say that PV over T equals K because it's constant, right? So PV over T equals to K. So therefore, if I plot a graph of PV over T versus anything, it will be a straight line. Okay, I repeat that. From this equation, if they are looking at 1 mole of gas, N is 1, R is a constant value 8.31. So this side over of the equation therefore becomes a constant. So PV against over T is K. It's always going to be K, right? So if I plot my y-axis PV over T against anything, so my y-axis is PV over T, I plot it against pressure, or I plot it against volume, or I plot it against temperature. No matter how the pressure changes, no matter how volume changes on the x-axis, and no matter how temperature changes on the x-axis, PV over T will never change because we just agreed that PV over T is a constant, right? So therefore, at low P is this value. At medium P is due this value. At very high P value is due this value. We are getting a straight line for this graph. Next, let's look at another graph. Now, if temperature is constant, so let's look at our equation PV equals nRT. N is 1, R 8.31. And if temperature is also constant, so this is constant, R is constant, T is a constant, so the whole thing now is a constant. So PV equals to constant, right? And so what's the relationship between PV against anything? So if I plot PV as my y-axis against anything like, for example, a changing pressure or a changing volume, it will be a straight line. Understand? But cannot be temperature because we already said temperature is constant, right? So if temperature is constant, the value of PV is equals to nRT, right? Which N is 1, R is 8.31, T is constant because we define temperature as constant. So therefore, this whole thing is a constant. Right, at low value is still decay. At high value is still K. So it's straight line regardless of the P or the V value changes. Next, what else can we see from the equation? If PV equal to nRT, N is 1, R is 8.31, and temperature is constant. So we can say PV equals to constant. So what's the relationship here is that if P is large, then V must be small. Right, just example, okay? Let's say, let the K be 6. So if P is 3, V is 2, you get 6. Right? So if P is 6, so P is large, then V has to be small in order to give you back 6. Right? If P is small, then V has to be large in order to give you back 6. So what we can see from this thing is that PV are inversely related. So when P is large, V has to be small. Right. So the relationship is P equals to K over V. So we are going to plot a P equals to K over V graph. So in this case, is P equals to KV minus 1 graph. So if I plot a P against V minus 1, it looks a straight line. So look carefully. If I'm plotting my y-axis is P, and my x-axis is 1 over V. So it looks like this. P is my y, and this is equals to K times 1 over V, right? So 1 over V is my x, and this is my M, so y equals to mx graph. So if I plot P against 1 over V as the axis, I will get a linear graph y equals to mx passing through origin. Okay, but what if I don't plot P against 1 over V? So look at the axis, this is 1 over V. But what if I just want to plot P against V? So if I plot P against V, I'm plotting this graph. P equals to KV minus 1. Right, so the shape will be a V minus 1 graph shape. So it will be this. So Y and my x is b raised to power. Okay, so I should plot a shape which is minus 1 graph. So it has a shape like this. So at constant temperature, the pressure is fixed. The pressure of a fixed amount of gas, which means fixed moles of gas, will be inversely proportional to the volume. So we can see that if temperature is constant, PV equals to nRT. N is 1 mole of gas, R is constant, T is constant, so we can say PV equals to constant, right? So PV is never going to change. So that means P1 times V1 should equals to P2 times V2. What do I mean by that? So under this set of condition, before I push the piston down, the pressure is so much, the volume is so much. So we call it P1 and V1. Then next, I give the piston push it down. So the pressure is another value. The volume is another value. So we call it P2 and V2. But because the moles of gas did not change and the temperature did not change, so therefore P1 times V1 should equals to P2 times V2. Okay, so let's put in some numbers. So let's say if this is 10 Newton per meter square, and this is 2 meter cube, right? So then this is a higher pressure, right? So pressure is 50 Newton per meter square. So find V2. So how will you do it? So 10 times 2 is equals to 50 times V2. So you'll find that you have only one unknown, that is V2. So 20 divided by 50 is V2. Can you see that? Okay. Now, can you see that in my example, I'm still using the same units as the ideal gas law units. But what if I change the units to something outrageous? Okay, in this context. So let's say if I call this 76 ATM. And then this is 102 ATM. And I don't want to use meter cube. I just want this to be cm cube. I put 120 cm cube. And this one, I don't know the volume, but I want the volume in cm cube. So remember, if you look carefully at this equation, when I press my calculator, I did not really key in 8.31. Right? I did not really key in 8.31 in solving the question. So there is no need to convert to the set of units this needed by the ideal gas because I'm not keying the value 8.31. So example, so for this case, I'll be using 76 times 120 equals to 102 times V2. I just take the values in their given units and sub in. It's fine. There's no need to convert because as long as the units on both sides are consistent. So this is ATM, this is ATM, this is cm cube, this should be in cm cube as long as it's consistent. Okay, but they can only skip the conversion of units only if you do not key in 8.31 into the calculator. And also, we are not looking at temperature cases. Because for temperature cases, regardless of what is the situation, you will have to convert units. Okay, so for temperature cases, we always have to convert units because temperature conversion is not by a multiple. It's by adding a number. Whereas for this case, ATM convert to Pascal or cm cube convert to meter cube. If I'm doing any conversion, it's by a multiple or by dividing by a factor. And it's always the same factor. Okay, so let's look at these cases. This case, I have 350 cm cube container. It has a pressure of so much. What is the volume of this gas at another pressure? So I do not need to convert units as long as the units are consistent. So that means the volume in this case must be cm cube. So I will just sub in blindly what I'm given. So I will just put in 103 kilopascal times 350 cm cube is equals to 150 kilopascal times volume in cm cube. Then you'll find that there's only one unknown, then you can find the answer in cm cube. Okay? So that was a case where the temperature was constant. Right? Can you see temperature constant? Now, what if this time round is not temperature? Let us make pressure constant. So if I make pressure constant and rearrange the equation, I will find that this is the case. K. So let's move the K all together on one side. So and then I will get P over T equals to NR over V. V over T is equals to NR over P. This is constant, this is constant, this is constant. So whole thing is now another constant. Okay, so that gives us another equation, V over T equals to K. So that means, right, if I have, as long as pressure is constant, if I have two experiments and they are at different volume and different temperature, when I sub it in V over T, it must give me back the same constant value because pressure is the same. Okay, and we can also see from here is that volume is directly proportional to temperature because you can see the equation is V equals to KT, Y equals to mx. So if I'm going to plot a graph of V against T, it should be a linear graph y equals to mx, right? But you look carefully, my V is my y-axis, my T is my x-axis, and this T must be in Kelvin. Okay, it's only linear if it's in Kelvin, right? But what if it's in degrees Celsius? So you can see that the graph passes to 0 Kelvin. The graph cuts the x-axis. So x-axis is the temperature, right? So the graph actually cuts the x-axis at 0 Kelvin. So if I'm going to translate it to temperature, that means I must have if I'm going to translate it to degrees Celsius, that means the graph must cut x-axis at negative 273 degrees Celsius, right? Because 0 Kelvin is minus 273 degrees Celsius. So what if I do not plot Kelvin as the scale on the x-axis? I plot it under degrees Celsius. You can do so, but just make sure that your graph cuts the x-axis at negative 273 degrees Celsius because it's supposed to cut at 0 Kelvin. Understand? Okay, this is in degrees Celsius and the other is in Kelvin. Now, also what can we see here is that V over T is always a constant. So therefore, if I have two different sets of conditions, V1, T1 should equals to K. And if I have another set of conditions, V2, T2 should also equals to K. And therefore, V1, T1 must equals to V2, T2 because both of them gives you K. Right? So that gives us the next equation. Remember previously we have one P1 V1 equals to P2 V2. This one, right? P1 V1 equals to P2 P1 V1 equals to P2 V2. So therefore, now we can also have another one, which is V1 T over T1 is equals to V2 over T2. Right? But the only thing is that for this equation, even though we did not sub in R, we still need to convert units for temperature. Remember, even though for this equation, I did not sub in R, but I will still have to convert units for temperature because temperature did not, converting from degrees Celsius to Kelvin is not by a multiple, it's by adding a factor. So therefore, we will have to convert. Okay, so let's look at this. Hydrogen gas occupies 692 dm³ at this degree Celsius. What volume will the gas occupy if it's cooled down? So if I let the volume be in dm³, as long as it's consistent, dm³ and dm³, I don't need to convert the volume. But no matter what, I will need to convert the temperature. Okay, so 592 must be converted to Kelvin. And 123 must be converted to Kelvin. Okay, so I can have 692 over 592 plus 273. So V1 over T1 equals to V2, which is unknown in dm³, because this is in dm³, over T2. The T2 is 123 plus 273. So solve the equation, find V2. So you have learned what happens if temperature and pressure are constant, right? So if temperature is constant, then we will have this equation P1 V1 equals to P2 V2. If pressure is constant, then we will have this equation V1 over T1 equals to V2 over T2, right? Now, what happens if volume is constant? So if volume is constant, remember PV equal nRT, right? Right. This is K, this is K, this is K. So let's rearrange, put the K all on one side. So P over T equals to K. Right. So P over T equals to K. That means P equals to K P. So if I plot P against T, so how will it look like? It will be a straight line passing through origin if the T is in Kelvin. If T is in Kelvin, then it will be through origin. But if T is in degrees Celsius, then you will plot. Remember, the graph cuts at 0 Kelvin. So the graph must cut at minus 273 degrees Celsius if temperature is in degrees Celsius. So the graph would be like this. Straight line cutting at this part. If this is P against temperature in degrees Celsius. Okay, so that gives us another formula. Remember just now we have V1 T1 equal V1 over T1 equals to V2 over T2, and we have P1 V1 equals to P2 V2. So we can have one more equation now. What's the equation? That's relating to P and T. Look at here. So we can have another equation, P1 T1 equals to P2 T2. So P can be in any units. They can be Newton per meter, they can be ATM, they can be Pascal, they can be in mmHg. As long as they are consistent, there's no need to convert, but temperature always must convert to Kelvin. Okay? Okay, so now we see some relationship. We also come out with a few equations. So let's summarize what are the equations that we have learned. We learned PV equals to nRT. We learned P1 V1 equals to P2 V2 under constant T. We learned V1 over T1 equals to V2 over T2 under constant T. We also learned P1 over T1 equals to P2 over T2 under constant volume. So we learn all this, right? So if we put all of these three equations together, you actually get the ideal gas equation. All right. Now, what else can we get from the ideal gas equations besides all this? We can also get MR. Why? Because PV equals to nRT. And what is N? N is number of moles, which is mass over mR. So we can replace the term N with M over mR, mass over mR, right? And we make mR the subject. mR equals to mRT over PV. So if I submit the mass multiplied by gas constant multiplied by temperature in Kelvin divided by pressure in Pascal, volume in meter cube, I will get the MR of the gas. Okay, so we can find MR. Now, besides MR, what else can we find? So you do see a term here known as mass. And we also see we have a term here, volume. So what do we learn about density? Density is mass over volume. So can we make M over V on one side? If we rearrange the equation to make M over V on one side, we will have P times MR over RT equals to mass over volume, which is density. So density will therefore be calculated by P times MR over RT. So it's from the same ideal gas equation formula that we can find the MR and can find density of a gas. Okay, so this is how they show you how to derive density. So we can see M over volume, mass over volume is density actually, right? So we can sub density into this term here. So M is equals to M over volume, RT times V. So M over volume is density. So we take the density to replace this term. And so we have density RT over P. All right, so these are some of the takeaways. Firstly, we have some assumptions of the ideal gas, the 5 assumptions, and the 2 conditions whereby a real gas will behave more ideally. And also, we also learn about the ideal gas equation and how we vary and manipulate the equation to come out with various graphs. And also from the ideal gas equations, under certain conditions where constant temperature, constant pressure, constant volume, we come up with new equations like P1 V1 equals to P2 V2, V1 over T1 equals to V2 over T2, and P1 over T1 equals to P2 over T2. So all these words derive from ideal gas equation, And from that, we can also see that from this equation, we can find density and MR. Okay? And there are things like real gases, and real gases do not behave ideally. And we can actually adjust a higher temperature to make it more ideal. We can also use a lower volume to make it more ideal. And also we can vary the nature of the gas, like some gases which has lower intermolecular forces. So it's easier for them to behave ideally because they will tend to follow the assumption that there's no intermolecular forces between the molecules. All right, so with that, we finished the theory on the ideal gases. So what you can do is you finish the video, you read through your school notes once, and you feel that if you're ready, then you can try the questions and give it a try and see whether you can apply what you've learned to solve the questions.